What we're going to do in section 4.3 applies something we discovered in section 4.2, which is that every vector space of n dimensions is isomorphic to Rn. What that means is that I can take an element in my vector space, which, for example, if we talk about the notes 4.3, would be quadratic functions. I can take an element of that vector space and change the quadratic function I have to a vector. And then I can apply a transformation to that vector and finally go back to quadratic functions. What's the advantage of that? Well, the advantage is we know well how to work with vectors. Vectors are ideal in linear algebra because we have matrices that apply the transformations perfectly. So instead of having a function that we transform to become another function, let's say we take the derivative, we are going to change that function to a vector and then apply a B matrix, which we are going to need to figure out what it is. And then after we've applied the B matrix to that vector, we're going to move back from our output vector to the function in the output space. So to achieve that goal that's represented by the orange arrow, we're going to have to find out what LB is. And that's not really hard because we're just going to identify the basis elements from my vector space of quadratic functions with basis elements in Rn, which are vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Secondly, we're going to need to build matrix B. In order to build matrix B, we're actually going to take the other route, which is going from the bottom left up, across, and down to the bottom right, represented here. So how do we do that? In order to build a matrix B, it's always the same. You want to figure out what the transforms of the basis vectors are. So let's say when I transform 1, 0, 0, I get 2, 3, negative 5, using the arrow that goes up, across, and down. That'll give me the first column in matrix B. And then again, with vector 0, 1, 0, I go up, across, and down, and I find, let's say, vector 0, 4, 1. So that's going to be my second column. And lastly, for the last vector in my basis, 0, 0, 1, I go up, across, and down, and I find, for example, it could be anything, I'm just making up numbers, 1, 1, 8, and therefore that's the last column in matrix B. So now that we would have LB, B, we can actually apply the orange arrow, which might be a little easier than going across with the blue arrow. And just in general, it's a much more efficient way because we can use matrices. So we're kind of formalizing the process, making it into some kind of machine that just takes a vector and spits out a vector on the other side. Okay, so with that introduction in mind, let's go over the notes using Eric Cheng's again. So here's the same sketch that I discussed just now, and the matrix B that we talked about is called the B matrix of the transformation. This B is kind of made a little bit funny, like you can see it here. So the B matrix. Okay, so I think the best is just to jump into an example to see how it works. These two examples are broken down into several steps that should really help us understand how we make the B matrix and then how we can use it. So, A, find the basis B of P2. P2 is the quadratic functions. It has 3 dimensions. So we want a basis, and that means we need 3 elements. Now, quadratic equations are f of x equals ax squared plus bx plus c. So we can see that the easiest way to create a basis is to take x squared, x, and 1. And then we can combine these using linear combinations, adding them and multiplying them by scalars to find any quadratic functions. For example, 7x squared plus 2x minus 8. So the basis B of the transformation, the best, the easiest, is just to choose x squared, x, and 1. But it's not the other way. It's not the only way. You could choose any 3 quadratic functions, provided that with any linear combination, it spans all the quadratic functions. So, write its counterpart in R3 through LB. So here, we're going to assign or identify each element in the basis of the quadratic functions to an element in the basis or standard basis of Rn. So we'll decide x squared is 1, 0, 0, x is 0, 1, 0, and 1 is 0, 0, 1. You could do it differently, for example, choosing 1, 0, 0 here, 0, 1, 0, and 0, 0, 1, whatever, as long as you're consistent. Now we're going to build matrix B column by column, and to do that, I need to check what happens to each of the standard basis elements. So what happens to these if I go up, across, and down from the introduction to this video? Well, that means vector 1, 0, 0, I'm actually interested in seeing what happens when I transform x squared, f of x equals x squared. So we haven't even talked about what the linear transformation is in this exercise. The transformation of the function is another function, which is f prime plus f double prime. So I take a quadratic function, and the output is the derivative plus the second derivative. So what is the output when I plug in x squared? The derivative is 2x, the second derivative is 2, so t of x squared equals 2x plus 2. Now I need to go, what we did here is going across. Now I need to go down again because I want to express that as a vector. The vector corresponding to 2x plus 2 is 0, because there's 0 of x squared, 2, and 2. So here it is. And that means my matrix B will have its first column being 0, 2, 2. Continuing with the same idea, we need to find the second column of B. So what is the image of 0, 1, 0? Meaning, what is t of x? Because that's the second element in my basis. So I take the derivative, the second derivative, and I find that t of x is equal to 1, and therefore 0, 1, 0 goes to 0x squared plus 0x plus 1. Finally, if I transform the last element in my basis, which is the function f of x equals 1, I take the derivative and the second derivative, it gives me 0 plus 0, so transforming 0, 0, 1 goes to 0, 0, 0. So there we have it. We can now show what matrix B is column by column. It's 0 to 2, 0, 0, 1, 0, 0, 0. So the notes that are written above and on the side show that this column is the transform of vector 1, 0, 0. This column is the transform of vector 0, 1, 0, and this column is the transform of vector 0, 0, 1. If you look at this matrix horizontally, row by row, you can read that the first row is the coefficients of x squared, the second row shows the coefficients in x, and the last row shows the constant coefficients. Okay, back to, so that's question C. Question D, use your matrix to find the transform of 3x squared plus 4x minus, 3x squared plus x minus 4. Of course, we're all capable of doing it just using derivatives, but we're trying to find kind of a formal way to maybe put it in a computer to do it. So here we can already know that if I just apply that, the answer is going to be 6x plus 1 plus 6. So the transform of this is going to be 6x plus 7. Let's see if it works with my matrix. Okay, so 3x squared plus 3 plus x minus 4 is actually the vector 3, 1, negative 4. So I'm going to multiply my B matrix with 3, 1, negative 4, and this is what I get. Yes, indeed, it's 0x squared plus 6x plus 7, so exactly what I expected. So here, if you think of the sketch, the little diagram, this step is going down, this multiplication is going across, and then that step here is going back up again, because I started with a quadratic function and I end with a quadratic function. Here we are a little bit tolerant. We call this a quadratic function because it has 0x squared, so it's acceptable. So now we have a few questions, E, F, G, H, that kind of help us reflect on concepts from previous sections. Find the basis of the kernel. That means what are the functions such that when I apply the transformation I get 0? What are functions that when I take the first derivative and add the second derivative I get 0? Well, it's all the functions that are constant. So I can write it either at the kernel of t is the span of 1, or the kernel of t is f of x equals c. Find the basis of the image. If you look at our results, you will see that we will never have any terms in x squared. So the image is the span of x and 1. Also, if you look at the B matrix, you can say that the image is the span of 2x plus 2 and 1. That's totally fine. There's different ways of expressing the image. This is the more standard way to just look at the columns of matrix B and say, well, it's the span of 2x plus 2 and 1. What I just said and this here, it spans the same subspace, so both are valid answers. So is T an isomorphism? No, for sure, because the kernel is not 0. Notice that you could also look at the image and say, well, the image is not 3, and it should be, the image should be as, take the whole space V, we see that we go from P2 in 3D to P2 in 3D, so the image should correspond to these two numbers. So does it make sense with the rank nullity theorem? Yes, 1 plus 2 equals 3. Here, that's what we should write here. 1 plus 2 equals 3. 3 being the dimension of the P2 here, not this one. Okay, similar example, A, B, C, D, E, F, G, H, exactly the same steps. Consider the linear transformation that takes a matrix and outputs another matrix, 2 by 2 matrices. This is how we write 2 by 2 matrices, the space of 2 by 2 matrices. So here, there's something that's not necessarily obvious. You might feel like, well, we've worked with matrices for 3 full chapters. Why is that new? Well, it's in fact very new, because the elements we were working with in chapters 1, 2, and 3 were always vectors. Vectors are the objects that we were moving around and transforming. We had lots of matrices in chapters 1, 2, and 3 because they were our transformation machines. In this example, what's very different is that my element is a matrix. So I'm taking a matrix and I'm transforming the matrix itself. I'm not transforming a vector. So here, this represents, well, we have a matrix and we transform it to another matrix. And what we're going to do is we're going to change that matrix to a vector, then apply a B matrix, which will actually be quite different from the 2 by 2 matrices that are the elements we work with, and then go back to a 2 by 2 matrix. You can maybe see here that the B matrix is actually a 4 by 4 matrix, not a 2 by 2 matrix. So question A, we have to write a standard basis for the 2 by 2 matrices, and the easiest way is just to put a 1 in for every entry, And with these 4 matrices, I span the entire vector space. I'm going to identify each of these to a vector in R4, because since our vector space has 4 dimensions, I'm going to have to work with R4. And obviously, I'm going to pick 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Here we listed them moving in from moving in rows. You could also go in columns. That's up to you. In order to build matrix B, I need to figure out what the transform of each basis element is. So for this basis element 1, 0, 0, 0, I'm going to plug in the original element in my basis and actually work through the problem entirely to see what the output is. So this is the transform, and that's what I get. 0, -1, 0, 0, if we read it in rows, is going to come as the first column in matrix B. If I transform the second element in my basis, I get 0, 0, 0, so that becomes the second column in matrix B. Same with the third, same with the fourth, and now we have been able to build matrix B. This should be just a B, not a squiggly B, but it doesn't matter. And now that we've built matrix B, we can actually apply it to other elements in the space of 2 by 2 matrices. So let's see what would happen to this matrix here. 4, 3, 2, 1 written red in rows. I just transform 4, 3, 2, 1 to a vector, and then I transform that using my B matrix, and this is the result. If we check that, because that's pretty easy to check, we can multiply just using the transformation, and we see that yes, we get the same result. It's the matrix 2, -3, 0, -2. Question E is to find the kernel of the transformation. So let's look at matrix B. Here we can just observe matrix B and find what the kernel is. We can see that if I have vector 0, 1, 0, 0, I'm gonna get the 0 vector. 0, 1, 0, 0 is going to yield 0, so that's an element of the kernel. And secondly, I can recognize that column 4 is negative column 1, so if I use vector 1, 0, 0, 1, I would also obtain the vector 0. So these two elements are in my kernel, and of course any combination of them is also in my kernel. So the kernel is the span of 0, 1, 0, 0 and 1, 0, 0, 1. For the image, I observe that we have 2 columns that are linearly independent in B, and that's the one I choose. 0, -1, 0, 0 and 1, 0, 0, -1 form are 2 elements that span my image. Is it an isomorphism? No, because the kernel is not 0, that's easy. And lastly, just checking the rank nullity theorem, well, it's 2, because there's 2 elements in my kernel, plus 2, because the dimension of the image is also 2. So 2 plus 2 equals 4, which is the dimension of the 2 by 2 matrices.